Whatever. It's
Does
better.
Zoom give you cloud space or something, or do you have to define like a cloud drive or something?
I have no idea. Maybe, with what I'm paying them every month, they give us some space.
Probably.
Right.
Yeah.
All right. So, where are we? Where's
We're on types, and this chapter was about the F sharp's algebraic type system, and also like how to use it, like how to make a composition of types to sort of define your domain model. So I thought it was kind of interesting approach. And I was like, conceptually, it's one of those things that's like not in and of itself hard to understand, but you can just totally imagine this situation where you're creating a type that's what, well, you know how to like, it's not, they stress it's not a class because it has no methods and stuff attached to it. It's just a data structure, but it's this potential transformation of data of types that I imagine you could get kind of lost in if you don't careful. But um,
Oh, I mean, for me, I love this. Like, this
right.
is one of my favorite things. In fact, when I was learning Elixir and I was getting into Elixir, and then I went and tried Elm, one of the things I loved so much about Elm was these algebraic types. And I was like, oh my God, like, why isn't this in Elixir? This is so awesome. Um, I mean, it really does do exactly what you want types to do, which is to allow you to do type checking, right?
Mm-hmm.
So the fact that you can make your own very specific type, like this thing only is going to take one of these three things or one of these two things, and I've defined it. It's not just an int; it's this kind of an int. Right?
Mm-hmm. Yeah, for sure. Yeah. Elm, Haskell, those kinds of languages. Yeah, and then F sharp was very. I mean, a lot of this stuff looks a lot like that. Even the type signatures they're using for the functions and stuff like that. One thing I'm really happy about right off the gate, but let's just get into it. Um, but that's kind of like what we just talked about, this tunnel of transformation. Um, they're saying a function is basically an input and output, right? But this is what made me happy. I didn't quite realize F sharp was built this way. One of the things let's pick on Elixir again. One of the things I very much don't like about Elixir is the sense of arity. So like a function that takes in two arguments or something like that. One thing I really really like about Haskell and Elm, really really like it, is that they have this built-in sense of currying where it's like, well, there's only such a thing. There's a function that takes in one argument, and it might produce a function that expects another argument and another function that expects another argument. So even if it looks like, and it's just all based on lambda calculus, exactly how lambda calculus works, which is the equivalent of Turing machines. So, but it's not this concept of here's a function that has three arguments. It's a function that takes in an argument and produces a function that expects an argument, which produces a function. It's like this kind of chain, and then you can just build things like that. Like just they do it right here. So they make a function called add one that expects x, which I wonder if we can even really do that. Let me just try in my.
Oh, an interactive.
Yeah, well, I'm gonna just try like I'm gonna try a function called um, add, and I'm gonna say add is. I
Why
don't know
don't
if
you
this is
put it
gonna
on the
work.
window that you're recording on so we can
Sure.
see you do it?
Oh yeah, I'm not on that window. All right, hang on. Let me try
You
to do
can
it.
just move it over that.
Oh well, I could try. Yeah, I think I can do that. Yeah, I could do it. Well, I just have like the remote desktop going. It's probably fine. Um, so let's try this. Just want to see if I could do this. I don't know if it'll let me, but um, let add one. What I want to do. Let's see. Um, Wait, let me. What I want to do is I want to just. I'm trying to think this through. So I want to have a function that just takes in an argument. I'm like kind of being stupid right now. I think this through. So add one should just be. So can I do? Oh yeah, okay. So let's say what is add? Yeah, this is what I want to try. Add one. That's right. Okay. So I can say. So I have now I could say add one equal add of one like that, right? Will that work? And then I can say add one of two. Nice. Okay.
Yeah.
So that yeah. So this is what I love. Like I'm like this is amazing because you can. So I just created a function here that only gave one of the arguments that it was defined as, not both of them, right? And it's because of that power of currying. So it's just like grab this part and it's waiting for that kind of like closure on the Y, and it's saying, okay, I'm just gonna be just sitting here returning a function that expects an int that is going to return. So this is just like Elm and Haskell. This looks like function definition right here, where expects with the parentheses being the function, expects an argument and it returns an int. Expects an int as an argument and it's going to return an int. This function. So this function add one itself is another function. So that's kind of what I was getting at. That I really am appreciative to see that because I don't like that Elixir doesn't have that. It really bugs me out. I think it would be so much cooler if it did, but it doesn't. So
yeah.
Anyway.
Well, this is coming from a much pure functional.
That's what I'm saying. That's exactly what I'm saying. It's like a pure functional type of approach.
All right, should we go through this?
Yeah, I was just looking at theirs and I was like, well, wait a minute. I thought I was looking at that thinking it was currying, and then as I was doing this, I was like, maybe they don't have it. And then I'm like, no, it has it because they didn't do it here, but it looks like it is, but it's not. But anyway, yeah. Sorry.
I think I can share while you're sharing.
Yeah. So why don't do you want to start?
What happens? What does that look like?
I don't know because, like, I guess what are you recording too when you hit record? Like, what is it actually recording?
Oh, it's recording whatever is on the screen, right? So
I don't know because I see like I have one screen that says you are screen sharing, and then I got this other 3 thumbnails that is me, you, and you, and I'm kind of
yeah. So right now, I see what's happening. I see what's going on. So I'm recording whatever is on the main. Actually, I don't know what I'm recording. But the point is that on the top where it says, oh, right. Okay. Never mind. I should stop screen sharing.
Oh, I can't even see if you're screen sharing, honestly.
Because you're screen sharing as well. But since I have a
third.
If I
stop?
Since I have a third, yeah. Since I have a third person.
Oh, I got it. Now I see it. Yeah.
Then I can see. Okay. I can see either one. I can choose. This is cool. All right. Anyway, you should screen share and share the.
What, the book or the code?
Book.
The book. Okay. All right. I'll share it on that screen just because my code has to be there too. You see the book?
Yeah.
Great. Okay. So this is something I had to figure out too. I mean, it just wasn't really that hard, but they just kind of talk about F#. I had like F# interactive needs the double semicolons, I guess, to end a statement.
Yeah.
But all right, whatever, no big deal. As you can see, the let keyword is used to define a function. The parameters are separated by spaces without parentheses or commas. this also what clued me into like their concept of possible currying was that I realized like this let function. I was like, well, how does it know like the name of this function? And that seems like a stupid question to ask because it's like, oh, well, it's just the first keyword in the thing, which I get that, but it's like it's sort of like, how like in a lot of languages you might say, oh, definition of function is this or whatever like that. Well, Elm and Haskell and F sharp don't do that. They just go boom, 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 and they just start throwing they throw arguments at you one after another. And I know that sounds kind of dumb because you just be like, oh, well, it's just the first one. That's the name. It's like, yeah, I get that. But something clued me into like, well, if I could just keep popping elements on the end, maybe they have this currying concept. So I don't know I don't know if it's related, but anyway. So unlike there's no return keyword, it's pretty typical functional stuff. The last expression in the function definition is the output. Even though F sharp cares about types of the inputs and outputs, you rarely need to explicitly declare them because in most cases the compiler is going to infer them automatically. For add one, the inferred type of X before the arrow is an int, and the inferred type of the output is also an int. So the type signature is int goes to int. I don't know how you say that exactly, but for add, the inferred type of X and Y is int, and the inferred type of the output is also int and has two parameters. So it's an int goes to an int returns a function that expects another int that returns a function. That returns the int itself as the last thing. If you're using an IDE such as Visual Studio, hover over the definition of a function will show you its type signature. But since this is a book, we'll put the signature in comments above the definition when we need to make it clear. It's just a comment and isn't used by the compiler. Functions consist of more than one line are written with an indent like Python. Interesting. There are no curly braces. Here is an example. So square plus 1x. So let me just do that. Okay. So square. So okay. So do you see my code now?
Yep.
Cool. Square plus 1 of x is okay. Let square of equals x times x, and I think they said square of x plus 1, something like this. I don't know if this is okay. So let's say square plus 1 of 2, so we should get 5, right? That's not how you spell square. Here we go. Yeah, okay, cool. And then 101. Sweet. What about negative 10 to be 101 as well? Cool. All right. Nice. That's how I do it. All right. This kind of throws me though, by the way, I'm not gonna lie, because I have never seen this before, this equals thing. This example shows you can define subfunctions, okay, and again, the last line, square plus 1 is the return value. Great. This part, the functions with generic types. If function will work with, well, not the any type is cool. Function will work with any type, the compiler will automatically refer generic type as the R equal function. R equals is this X equals Y. That's what threw me. I never seen that before.
No, doesn't not. I mean, I think Elm's the same, right?
It's not a double. It's not like a double equals or anything. I don't remember.
Equals is equality.
Interesting. Yeah, I mean, it would make sense if they're the same as like Haskell and Elm.
I'm pretty sure. But yeah.
Let me see. Let's just see this. This is probably. See, not in Haskell, so maybe just Elm does it.
Yeah, maybe I'm just tripping.
Well, here's like comparisons. Yeah, I don't know. Nah, it's double equals. But I never. Yeah, I mean, you see it. You see?
Yeah.
Um, yeah, all right. I can't like I never know what my I think I'm sharing the screen, but I've screwed that up many times. So, um, normally I would just run Elm Interactive, but it's been so long. I think I need an Elm project to do it in or something, so I didn't want to pull that up. But yeah, anyway, like I just kind of I think the part that throws me about that is that you have it here, and I'm trying to like under. I guess if you don't have the let keyword, I guess that makes sense. Like this doesn't have a let in front of it, so it's not like it's setting anything. Okay, I guess I can dig it. So for r equal, the inferred type of x and y is this tick a. The tick then letter is F sharp's way of indicating a generic type, and it's true since x and y could be any type as long as they are the same type. So because of that, I guess. Well, actually, probably because of this. Probably they need to be able to be compared. But yeah, definitely in the type signature, it explicitly says it. But I think if you ran this, it would force this. I'm pretty sure. We could try it. Let's just try it. R, R equal is X is Y. Yeah, so there are the two types. That's what I was looking for, equality. Or, well, so I don't really know. This is where I have a lot to learn in this department, but the category theory of this stuff where it's like, well, equality is part of a comparison type, and the comparison type is part of an orderable type or something like that. So I was kind of expecting to see something like that, but
We can leave category theory out of this. This is chapter 2.
yeah, yeah, right. Yeah. But
All right.
uh,
All right, let's move on.
and then they just kind of talk about another generic type, which I guess this is C sharp maybe, but it looks a lot like any of the TypeScript, for example, or whatever, where you have this generic T, which you obviously know
Yeah.
that. Okay. Do you wanna take over? Sorry.
Sure. So in programming languages like F sharp, types play a key role. So let's look at what they mean. A type in functional programming is not the same as a class, and object-oriented is much simpler. In fact, a type is just a name given to the set of possible values that can be used as inputs or outputs of a function. So this makes sense. It's a set of inputs, set of outputs. For example, we might take the set of numbers in the range negative 32,768 to positive 32,767, give them the label int 16. There's no special meaning, it's just the set. Okay. So there's the set, that's the set. This type is what determines the function signature. So the signature function might look like this. It takes in int 16 and outputs something else. This one outputs a string. So these here, the set of things in a type don't have to be primitive types. Primitive objects, for example, we may have a function that works with a set of objects that we've collectively called a person. So this is a set of types, people, person. From a conceptual point of view, the things in the type can be any kind of thing, real or virtual. The figure on page 63 shows a function that works with fruit. Whether these are real fruit, virtual representation isn't important right now. So this is the type of fruit, and they're going to show us here. Finally, functions are things too, so we can use sets of functions as a type as well. So the function below outputs something that is a fruit to fruit function.
That's pretty cool.
Yeah. So this takes in a set of valid inputs, something happens in here, and the output is one of these types, is another function that
Yeah.
converts apples to bananas, bananas to cherries, or cherries to lemons. Each element in the output set is a fruit-to-fruit function. So the signature of the function as a whole is like this, some input type, and it outputs a function, which is a fruit to a fruit. And they demarcate the function by putting it within these parens. So
Right.
this is really nice, this jargon. Values versus objects versus variables. In a functional programming language, most things are called values. In an object-oriented language, most things are called objects. So what is the difference between a value and an object? Value is just a member of a type, something that can be used as an input or an output. For example, 1 is a value of type int. ABC is a value of type string, and so on. Functions can be values as well. If we define a simple function such as let add 1 x equal to x plus 1, then add 1 is a function value of type int to int. Values are immutable, which is why they're not called variables, and values do not have any behavior attached to them, they're just data. In contrast, an object is an encapsulation of data structure and its associated behavior methods. In general, objects are expected to have state, that is, be mutable, and all operations that change that internal state must be provided by the object itself via dot notation. So in the world of functional programming, when objects don't exist, you should use the term value rather than variable or object. All right, you want to take it from me?
Sure. You'll hear the word composition used a lot in functional programming. It's the foundation of functional design. Composition just means that you can combine two things, make a bigger thing, like using Lego blocks. In the functional programming world, we use composition to build new functions from smaller functions and new types from smaller types. We'll talk about composition of types right now. We'll talk about function composition later. In F#, new types are built from smaller types in two ways, by anding them together or ORing them together. So anding them together. By the way, I mean, I was thinking about this and I was like trying to think, how did it I mean, it makes total sense, right? But I was even thinking about like Venn diagrams, and if you and things together, you get the intersection of them. And then you start to think about like, well, if I have these two events in the world and I have like this event happens and this event happens, what's the chances that they both happen? You end up multiplying their chances together effectively. And then when you OR them together, you're sort of adding the chances together.
When they say product.
Right, exactly. When they say product, when they say product or sum,
I was
right.
wondering why they call it the product and the.
That's what you're right. I forgot that they were going to say that, but that's,
yeah, we'll get there. We'll get there.
Yeah. I forgot that part.
All right, right.
Okay.
Let's see how they build the and type.
Sure, yeah. Let's start by building types using and. For example, we might say to make a fruit salad, you need apple and a banana and some cherries. In F#, this type is called a record, also what they call it in Haskell. Here's how the definition of fruit salad, and I think fruit salad record type would be written in F#. A fruit salad looks, I don't know, want to pick a name, mess up the name, but basically looks like some sort of dictionary where you have some key and some value. Okay, but anyway, it's a record. The curly braces indicate there's a record type, and the three fields are apple, banana, and cherries. And you can see there of each variety of those things, which we'll get to. The curly braces indicate that it's a record type. Okay, yeah. The OR types. The other way of building new types is by using OR. For example, you might say a fruit snack. If you're going to have a fruit snack, you need an apple or a banana or some cherries, a choice of those things. So one each from those things for the and type, and a choice of those things from the OR type.
Your mic seemed to get a little bit low. I don't know.
Oh, did it? Really?
Like the way you're turning your head or something.
Well, I have my. Okay. Hold on. Let me.
Maybe.
Let me just.
I can turn my volume up.
Well, I don't know why. What the hell's wrong? I don't know how to use Zoom. I'm trying here. Let's see. Show small active speaker vid. No, that's not right. That's not right.
Don't worry, I hear you. I turned my volume up. It's fine.
There's got to be a way. I just don't know. Sorry. Yeah, just let me know. Okay. These kinds of choice types will be incredibly useful for modeling, as we will see throughout the book. Here's the definition of a fruit snack using a choice type. Type fruit snack. It uses these vertical bars and says it's going to be an apple of the apple variety compared to the one up here. A banana of the banana variety and cherries of a cherry variety. So I think it's just a way of setting this as a value. But the choice type like this is called a discriminated union in F sharps. So again, a union, if you have like a U, is if you imagine the Venn diagram, it's the whole thing, all of it together. You color in the entire thing, including the intersection, and that's you get a union. It can be read like this: a fruit snack is either apple variety tagged with apple, or a banana variety tagged with banana, or a cherry variety tagged with cherries. The vertical bar separates each choice in the tag, such as apple and banana are needed because sometimes this I did not understand this. I read this sentence and I was like, I understand what they're saying, but I want to know how this can happen. So they said the vertical bar separates each choice in the tag, such as apple and banana, are needed because sometimes the two or more choices, so these two or more choices, may have the same type, and so tags are needed to distinguish them. So I got a little confused there. So how can multiple ones have the same type? How might that happen? Is it like a hierarchy or something maybe?
So I think it'll be clear if you go further, but I think that it'll be clear if we just think of it like fruit salad, actually. Like, you can have two things be of apple variety.
Right. So if okay, so we have the apple variety down here, which they just say not so we're not getting ahead of ourselves. The varieties of fruit are defined as types, which are used similarly to an enum in other languages or whatever. So like what you just said. So there's three apple varieties. So like this fruit snack came in here. Let's just say there were two of these things. It's like apple 1 of apple variety, apple 2 of apple variety, or something like that, right? So then a Golden Delicious comes in, and I guess it matches on apple 1, but it would never match on apple 2. So that's the part that's throwing me, I guess. I don't know. I kind of wasn't too worried about it because I felt like.
Sure, now that you. Right.
I'm very curious, like, and I can see as they do type composition, there probably are things that, well, there clearly are that I'm not thinking of, but I just couldn't think of it like right away. Is all I really meant. But anyway, I'm sure we're gonna understand that more and more. Do you want me to keep going? You want to pause?
Yeah, why don't you keep going?
Okay. So these are similar to enums in other languages. So the fruit themselves are OR types. And notice they don't have what do they call it? What do they call this word? A tag. They don't have tags. So they just are an enum. They are a collection of stuff. This can be read as an apple variety. Apple variety is either a Golden Delicious or a Granny Smith or a Fuji, and so on. The types that are built using ands are called product types. The types that are built using or are called sum types or tagged unions, or in F# terminology, discriminated unions. In this book, I will often call them choice types because I think that best describes their role in domain modeling. And yeah, I was sitting there thinking about that. I was like, ooh, that's really interesting. Why are they calling them products? Why are they calling them sums? And I started writing out, and then I let me see if I could. Well, this is gonna be hard to see, but let's see. Where's my camera? Okay.
Well, yeah, you'd have to stop sharing. So
Oh,
that
you.
you're
Oh,
up.
never mind. It's not a big deal. It's just basically the sum union is basically like probability of A plus the probability of B minus the probability of A
Right.
and B or whatever. And then the intersection one is really just like the probability of A given B times the probability of B. But the point is, one of them is adding and one of them is multiplying.
Right. I
And
think that is probably why they did it. It's
yeah, yeah. Okay, so I think you're up.
All right, let's say simple types. We will often define a choice type with only one choice, such as this. Type product code is going to be equal to product code of string. This type is almost always simplified to this. Type product code equals product code of string. Why would we create such a type? Because it's an easy way to create a wrapper, a type that contains a primitive, such as a string or int, as an inner value. We'll be seeing a lot of these kinds of types when we do domain modeling. In this book, I will label these single case unions as simple types as opposed to compound types like records and discriminated unions. More discussion of them is available, blah, blah, blah. Yeah, I love this because it's basically a really great way to kind of document your code with code, rather than documentation, which can become outdated. You're taking in a string, but you're saying this is what this string is, and it I think just helps simplify reading it.
Yeah. Do you know off the top by chance if like it says string or whatever and the other one said int, but previously they referenced like different types of those, like int 16s or 32s or whatever.
Yeah.
You could probably do that, right? If you wanted to.
Oh yeah.
Yeah, I'm sure you can.
Yeah, I think those are primitive F# types.
Yeah, exactly. Yeah.
Yeah, I mean, if you go into your interactive over there, and you just start typing int, I think you'll get a list of all the.
So when I.
Oh, okay. So mine works differently, I guess.
So as soon as you start typing in the interactive, you see things pop up.
Yeah, I can share.
I think I might have shut like Windows down and stuff or whatever, if that makes sense. I have to learn how to use this thing.
Yeah, if you make some errors in the interactive, then it stops being as interactive. Like if you write a bunch of lines without the semicolons and then realize that you need to put 2 semicolons and throw a bunch of garbage down there, you kind of mess it up. That happens.
Right.
But I just closed out and restarted Visual Studio. But here, if you let me share here a second.
Yeah.
Right here. So if I type in, for example.
Oh, no kidding.
All the different N64, N16, and 8.
Oh, totally. I'll try to get that going.
Yeah, but you should. Here, I'm gonna stop sharing.
I have no idea how to do that.
I would just close out F# and reopen.
Okay. You mean the Visual Studio? Like shut Visual Studio
Yeah,
down.
sorry. Visual Studio.
All right. Let's see. I feel like maybe I'm like missing something. Projects loaded, ready to use. Okay. Yeah, yeah, no, it doesn't do it. I must be missing. That's okay. I'll look into it.
You want to share a screen?
Yeah. Yeah, I'll look into it. I mean, this stuff works, which is good, but the one down here doesn't seem to do that.
One other thing is that Visual Studio sent me a message today saying that there was an update. Did I want to upgrade?
And you did
And I
it?
said sure. So maybe that's like the latest edition.
Okay. I'll look into it. Yeah. Yeah, definitely. I mean, I want to start using this anyway. I have it, and I'm starting to do more with some different Microsoft products. So, okay, no
Let's
problem.
get going to this next stuff here. Algebraic type system.
Okay. Um, okay. Do you want me to?
Yeah, go ahead.
Okay. Now we can define what we mean by algebraic type system. It's not as scary as it sounds. An algebraic type system is simply one where every compound type is composed from smaller types by anding or oring them together. F sharp, like most functional languages, but unlike OO languages, has a built-in algebraic type system. Using and using and or to build new data types should feel familiar. We use the same kind of and or to document our domain. We'll see shortly that an algebraic type system is indeed an excellent tool for domain modeling. Here we go. Why don't you take it, because it's got some good stuff.
All right, working with F-sharp types. In F-sharp, the way that types are defined and the way that they're constructed are very similar. For example, to define a record type, we use curly braces and then name, type, definitions for each field.
Like, do you have the book, by the way, on you? Can I move this?
Yeah, go ahead.
Okay, cool.
Type person is equal to curly brace first, string, semicolon, last, string, close curly brace.
Oh, Jesus. I'm guessing I gotta go like that, right? Okay.
Yeah, there you go. To construct a value of this type, we use the same curly braces, but use equal to assign a value to a field like this. I feel like this kind of stuff is like where they just make confusing rules, but you know.
I know, there's just rules. And, yeah, I got you.
You know, it's like colon is for assignment, equal is for.
Yeah, I know.
I don't even know.
You know what's interesting though, like this a person one. What's interesting to me about that is that like how did it know, like if you see in my interactive, it knew. There's got to be some sort of symbolic like reconstruction, because it knew that any like something of that is a person. You know what I'm saying? Like I created a record. Like I didn't tell a person that this is a person. You know what I mean? I just literally said.
You said first is equal to Alex and last is equal to is Adam, and
yeah,
it already has here that a type, a record of first and last,
right,
is already a defined type.
Right. That's what I'm kind of getting at. Yeah, it's got like this type hierarchy, and that's interesting. So, but does that mean that you can't, like, if I were to make something else that had first, last, and middle, right? Could I make a different record that had those things? And then if I gave it this, it would match up with person and not like, you know what I'm saying? Like if I made like person 2 and I said, it's got a first, which is a string, a middle, which is also a string, and a last, which is also a string, right? Like that. And then I said let B person, and I assume it's going to say it's person two, where I say first is John, middle equals Daniel, whatever, and last is Corey, right? Something like that. And I think it's just going to say that this is person two, which it does. So it's like, it's not as simple as just saying, oh, well, it's a first. It's like the entire record. It
Yeah.
like has to know that it matches the entire record, which
Right. See, like, here's the question. Can you do let C person equal first string, last string?
Okay, so let C person equal
Oh,
what?
sorry, person three, actually. Sorry. Let person three.
Oh. Yeah. So you're saying basically copy one of them exactly, right?
Right. It's gonna, I mean, I'm guessing it'll just override the definition.
Yeah, I think that's exactly what'll happen. Yeah.
Now, just type. Oh, I see.
Did
Okay, wait.
wait, what did I do wrong? Oh, this one. I didn't need that. No. The hell? Oh, I know. It's because it's because this is supposed to be a type. I can't
Right. Yeah.
type.
Okay. So now just type a person and see what type it comes up as.
Yeah, I mean that.
Double
Oops,
quote.
that was defined before though. Can we like make a new one?
All right. So it didn't override it though. Like,
No, but like what if I did this? Like let's just make a. Do I have I had a B person already? I can't
you
remember.
did, yeah.
Oh, I did. Okay. Um. So let's say
Give him
this
a first
is,
and last name.
yeah. Let's just do that. And I'm curious, what will this do? Okay, so this made it. It kind of did override it, right? Because it made it. But it's all about the compilation order, I guess.
Yeah.
So this made it a person three.
So let's try this. A person equals C person. Oh, sorry, no. Person equals person three.
Okay, it's interesting. Am I not allowed to do
Let's
that?
use our R equal.
What?
Let's use our R equal function we defined earlier.
Wait, what's that? I don't think I did that.
Yeah, you made it.
Uh,
Just called it R equal.
I restarted it though.
Restart. Okay, so let's remake that function.
Oh, I know what you're talking about. Okay. All right. So,
It's let R equal X, Y equals next line parens X equals.
oh, yeah, I got it. Yeah. Okay.
Yeah.
So then you're saying R equal person and person three, right?
Was the first one called person? Is that what it
I think.
Yeah.
I don't know how I don't know how to like.
So person.
If I had your thing, I'd be able to.
So it's interesting. Person is no longer defined.
A what? It's a constructor. Person is not defined, meaning like I can't use it as a function or something, which is interesting because it's just a type, I guess. I don't know.
All right, so let's try this last one, and then we move on. Let's try person D. Let person D equal.
Wait. Are you talking about a type or?
No.
Okay.
Let person D equal first Alex last atoms.
Oh, is this exactly what the other one was?
That's what a person is. Yeah.
Okay. Okay. Gotcha. All right. Yeah, I mean, I imagine it's gonna work just because it's gonna it's like in a different, I don't want to call it, it's in a different value, let's call it. Okay, so it's a person three.
All right. So
And
let's do R equal a person, B person.
R equal. Oh yeah, that's good. That's a good one.
So now I have two different types, but they have the exact same.
The expression was
Oh,
expected.
they're
Yeah,
different
yeah, yeah,
types.
yeah, yeah. So they're not equal. Yeah, yeah, yeah. Yeah, because R equal. So R equals type signature won't even let this happen.
Right. Right. Okay. Cool. All
That's kind
right.
of interesting. Yeah, yeah, yeah.
So
Okay,
now,
we proved something.
yeah, yeah, that I forgot about types. So, then now the next thing is very cool. This is pattern matching, right?
Deconstruction. Yeah, 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 yeah. Dude, we do this in Java. You can do this in Python. Not quite like this, but you can deconstruct the list. But in JavaScript, you can do this. You can actually do like object deconstruction, which is
Yeah,
kind of neat.
yeah, that's new. They've
It
added that.
is new. Yeah, yeah.
Yeah, so you can
It's way
let.
better here, though. I mean,
So we can do, yeah, right, exactly. Let last equal. But let's make it more explicit and just don't even have the words first and last. Let's just call them
what do you mean?
F1, just F and L.
For
For
like this? You
yeah,
mean?
yeah, it has to be that, right? Because that's what it's setting to.
Right.
Yeah, is equal to a person.
Oh shit.
Let's forget that.
This expression is expected to have person three, but it has type person.
Oh
What?
yeah, I think we really
'Cause-
messed up with.
No
Let's
shit.
just do yeah, D person. All right, there we go.
No, it didn't work.
Yeah, value L is atoms and value F is string.
Oh, it just
Is
gave me a
that
warning.
yeah?
What the fuck? The field
I think
labels.
we messed with it. We broke F sharp on our
um.
first try. Man, Microsoft, we're ready for jobs.
Yeah.
We broke your F sharp.
What the hell happened, man? And there was a reset. Oh yeah, reset interactive session. Jesus Christ, man. Hold on, like that. That was rough.
Interactives are always,
Yeah, yeah, exactly.
a
Okay.
little buggy, but it's
All
fine.
right. So let's just say, and then the A person was Alex Jones or something.
Alex Adams.
Alex Adams. Okay. Not S. There we go. All right, I'm almost there. And then
Oh, there you had it.
yeah, and then just change that. All right.
All right, cool.
Did something right.
Now we L.
Yep.
Yeah. But now they show you, oh, but wait, we didn't have to do that. We could have just let first equal to a person dot first.
Yeah. Yeah, you could do that too. Yeah. That makes, oh Jesus, I'm never gonna remember this.
Yeah.
Okay.
Oh, the doubles.
Yeah, I'm not struggling.
Just in the interactive,
It reminds me, I mean, this is the worst thing I'm gonna say about F sharp. I'm gonna say right now, and I know it's just the interactive, but doing that reminds me of coding in VBA. That's the worst thing I'm gonna say about F sharp ever in my life, I think, because yeah.
All right, so let's see what's going on now. Should we go back to the book?
Yep. Oh yeah, sorry.
The symmetry between construction and deconstruction applies to discriminated unions as well. All right, here we go. Unions as well. To define a choice type, We use the vertical bar to separate each choice, with each choice defined as case label of the type, like this. Type order quantity is equal to a unit quantity of int or a kilogram quantity of decimal. The choice type is constructed by using any one of the case labels as a constructor function with the associated information passed in as a parameter, like this. Let any order quantity in units equal to unit quantity 10. Let any order quantity in kilogram equal to kilogram quantity 2.5.
Yeah, I thought this was kind of wild too, actually. I struggled like really thinking of how this would work because you have this type order quantity and you have the case label of unit quantity, and and they're saying you can use that actually as a constructor itself. So I just want to try that because like
Yeah.
I was kind of not sure how that. This is even more so than what we were trying to do. I was kind of like, how the hell does this work? So unit quantity, and we can test this pretty easily, I think. Yeah. Kilogram quantity titty of decimal. Okay, that sounds good. And then unit quantity 10, just like that. Okay, cool. So what I wanted to try is say something like this, and then just unit, and now I'm going to break the interactive again. Of, let's just say something like that. Okay, so if I go unit, oh, I probably didn't break it though. Oh, all right. So if I go 10, it'll oh no, I did. Okay. So I redefined it.
So what? Can you do it as a string now?
Let's see. Yeah. Yeah. So it even says like which one it belongs to. It's kind of interesting. So I guess you just have to be careful that you're not like, if you're, I mean, I'm sure there's an architecture of having to do that, but you just got to be careful you don't name things, the same.
Yeah, namespace stuff.
Interesting.
All
Okay.
right, so let's see. Cases are not the same as subclasses. Unit quantity and kilogram quantity are not types themselves. They're just distinct cases of the order quantity type. In the example above, both these values have the same type, order quantity. To deconstruct a choice type, we must use pattern matching. The match ... with syntax with a test for each case like this. Let print quantity take an argument a order quantity equals match a order quantity with either unit quantity and then do something, printf that unit, or kilogram quantity, take in that variable as a kilogram quantity and do something with that. So yeah, this matching is great. It's a lot of fun.
Oh, okay. So if you do that, you do something like unit quantity, whatever, it doesn't even change. It just stays as that thing. So if you're passing that in, where is it? So if, even though it's saying, it's not like doing anything, it's just like saying, oh, it's a unit quantity 10 or kilogram quantity 2.5. You know what I mean? It is one thing. And then it's like you're passing it an order quantity in, and it's just literally matching on those two things. It's matching on the whatever the case label and the value, and then the other case label and the value. And if it matches unit quantity and pretty much anything, and kilogram quantity and pretty much anything, it'll just do whatever's on after the arrow. I mean, that's cool. what do you call it? Elixir has something like this too in its cond and case statements.
Yeah.
You know, I don't know that I've seen this. I know Rust does this, very close to this, but I don't know. Huh. I can't remember. I think Elm uses a case as well, doesn't it? I feel like it does.
Yeah, I don't remember. I mean, it does something like this.
It's something like this. Yeah. Takes in this value, matches it to one of these heads, and then does whatever comes after the arrow.
Right. So we can read this. As part of the matching process, any data associated with a particular case is also made available. In the above example, the U quantity value will be set if the input matches the unit quantity case.
That's kind of cool. So you're pulling, so because you're matching unit quantity and the value, and you're saying, okay, I can do something with this, just this pure value now.
Right.
It's not part of this
Pattern
type anymore. Yeah. Pretty good. Pretty cool.
Right. Here's the result of the pattern match. Well, yeah, when we pass in the two values. Print in order quantity 10 units, 2.5 kilograms. All right, building a domain model by composing types.
Do you want me to read it?
Yeah, let's. Yeah.
A composable type system is a great aid for doing domain-driven design because we can quickly create a complex model simply by mixing types together in different combinations. For example, say that we want to track payments for an e-commerce site. Let's see how this might be sketched out in code during a design session. First, we start with some wrappers for the primitive types, such as check number. These are simple types that we discussed above. Doing this gives them meaningful names and makes the rest of the domain easier to understand, as you said. Check number. So type check number is a check number of int. Type card number is a card number of int. So I guess that basically means if I were to, it's exactly what we just saw, literally. So if I were to write that, right, and then I gave a check number 10 like that, it just wraps that value with some check number type basically.
Right. Yeah, C has this with aliases. Well, I think they call them types actually. And in C code, people actually use this a lot. Like they'll rename ints.
Like just a simple type.
Like, yeah, they'll rename int some name that they want to give it because it's helpful in the code. That kind of got lost in the later
languages. Next, we build up some low-level types. A card type is an OR type, a choice between a Visa or MasterCard, while a credit card info is an AND type, a record containing a card type and a number type. So that's interesting. Let me do that. Okay, so I have a card type that is a Visa or a MasterCard, which is super interesting because I never defined Visa or MasterCard. And then the next one is credit card info, which is both of those things. Okay, I guess I could have just.
I think you need a curly brace.
I know I screwed up. Okay. All right. Let me just go. Bastard. The fucking. You know what? It's like easier if I just. Oh, okay. I got it. All right. I'm like looking at it, trying to figure out what the hell's going on here. Oh, that's interesting. They didn't let me. I can't go to the next line. All right. Forget that. Hold on a second. Let me just do this over. I'm sorry. It was really pathetic. All right. How did they? Of course. Okay. All right. Card type. They had a space in between them, didn't they? I guess I don't know if it matters, but okay.
I don't think it matters.
card type. Then they have nothing. Okay. And then what was the other one? The card number. Card number like this and like this. And there we go. Okie dokie. We then define another OR type payment method as a choice between cash, check, or card. This is no longer a simple enum because some of the choices have data associated with them. The check case has a check number, and the card case has credit card info. Okay, so check number. Did we? Oh, we did. Check number is an int, and credit card info is a card type, which is either Visa or MasterCard, and a card number, which is a string. Very nice, very nice. Okay, so I'll just start here, and is it cash? Let me just move this over for a sec. And I have this. Okay. So cash and check of check number and card of credit card info, which I defined above. Cool. We then can define a few more basic types. I'll move it over in a sec. Just such as payment activity and currency. So payment activity and currency. You're going to have a whole e-commerce site in a moment. And finally,
to go with a simple example of this story.
And finally, the top level payment is a record containing a payment amount and a currency and a payment method. So
I don't think these guys get it yet. Can we throw in Euro and USD just to make sure?
yeah. Amount is payment amount, which is the one above.
And rubles. Can you give me more currencies, please?
Currency. I know we don't have enough currencies, man.
If you can't pay in rubles.
What kind of crappy e-commerce site is this here? They don't even have Bitcoin, man. I mean, oh, it's funny. In the book, they actually do have that colon, like sometimes spaced, sometimes not. In mind. So I guess it doesn't really matter. Okay. So now we have all those things. So there you go. In about 25 lines of code, we have a pretty useful set of types already. I think I get it. So we have a payment amount. So let's just tracing it back real quick. So we have a payment. In that payment, we have an amount, a currency, and a method of payment. So we have payment amount. The payment amount is just a decimal. That's great. Currency is one of these two things. And then the method is where we trace it back, where it's one of these three. If it's cash, I don't know what that means. I guess it's just cash. If it's check, it's a check number, which was defined up here as an integer. And if it's a card, then it's got credit card info that has a card type, which is Visa or MasterCard, and a card number, which is a string. Cool. Of course, oh boy, here we go. Of course, there is no behavior directly associated with these types because this is a functional model, not an object-oriented model. To document the actions that can be taken, we instead define types that represent functions. So, for example, so this is where you come up with your type signatures and whatnot. So, for example, if we want to show that there's a way to use a payment type to pay for an unpaid invoice where the final result is a paid invoice, we could define a function that looks like this, type pay invoice, real quick. So type pay invoice is this. Nope, it's not.
I don't think that this is you can actually put this in the immediate. I think they're just giving you the type signature of what that function would look like.
God damn it. All right. We could define a function type. Oh, okay. But it's just weird that they wrote it like that, though.
Yeah, I think so. Maybe I'm mistaken.
Well, the only thing that got thrown was that it didn't know what this was. So so in other words, if I did like do I have payment? I did define payment. So
Well, why don't you
if I did something
do the
like
one below,
this,
which has payment currency to payment?
we have them all?
Yeah, we should.
Yeah, I was gonna say like I think it's just because of this stuff. Like you need to have the right payment, currency, and payment. Yeah. Right. Okay. Okay. So that was that, right?
Don't forget the equals there.
Yeah. Otherwise, I'll be doing it all over again. Yeah. Okay.
It does work.
Yeah. I mean, okay. So I guess this is just a function, right? That expects a payment, returns a function that expects a currency, and then returns that amount of money in that currency. Hey, dude, what's up? I am good. Can you lock that, please? Thanks. Yeah, okay. That's kind of awesome. I'm trying to think. I guess you would just, I mean, I guess instead of writing all this out in a function, signature or whatever, you would just write this maybe. I don't know. Where the payment is the input, the second parameter currency is the currency to convert to, and the second payment, the output, is the result after conversion. Yeah, I think we'll use
No
these. I'm
idea
sure
what
we will.
to do.
What's that?
I
Sorry.
have no idea what that would do. Like,
So I think if you were defining a function like not named this, right? Like a function called I don't know, pay for invoice or something like that. And you said pay like so let's say convert payment currency. Uh so let's say let convert I don't know how to do type signatures in F sharp, honestly. Um I I'm not really sure how you do it, but but I think what you would do is you would say, convert would take in
I don't think
this.
we do type signatures. I think the compiler always figures them out.
Oh, you never write them?
I don't think so. Yeah.
Okay.
I see what you're saying. Like, you want to create a function that is of that type.
Yeah.
Let's glaze over this in the interest of
Yeah, I think we'll know how to do it
on it.
better. They'll tell us the right path. Yeah, I agree with you on that. But like I know in Haskell and Elm, you definitely can't do it in the interactive. You're right about that. But in Haskell and Elm, you would do it in the file itself. Um, yeah, that's all I know. All right. So this modeling option. Oh yeah, this is interesting. I like their shorthand for this too, by the way.
Hold on, let's take a 2-minute pause, can we?
Yeah, I got something to drink myself.
All right, so modeling optional. Is it me or is it you?
You're up.
So modeling optional values, errors, and collections. While we were discussing domain modeling, let's talk about some common situations and how to represent them with the F# type system, namely optional or missing values, errors, functions that return no value, collections. Okay, so first, modeling optional values. The types that we have used so far, records and choice types, are not allowed to be null in F#. That means that every time we reference a type in a domain model, it is a required value. So how can we model missing or optional data? The answer is to think about what missing data means. It's either present or absent. There's something there or nothing there. We can model this with a choice type called option.
We've seen these kinds of things, you and me.
Yeah.
The maybe
Defined
types.
like this. Type option tick A is equal to either sum of tick A or none of that. So
tick A is generic. Could be anything.
some case means that, right, tick A is generic. Some case means that there's data stored in the associated values A. The none case means that there's no data. Again, the tick in tick A is F sharp's way of indicating a generic type. That is, the option type can be used to wrap any other type. C# or Java equivalent would be something like option T. You don't need to define the option type yourself. It's part of the standard F# library, and it has a rich set of helper functions that work with it. To indicate optional data in the domain model, then, we wrap the type in option, just as we would in C# or Java. For example, if we have a personal name type, and the first and last names are required, but the middle initial is optional, we could model it like this.
See, that's how you would have done what we were trying to do before. You would just say person, and you'd put a middle initial or whatever as an optional type, and then it would always match on the right one.
So, right, yeah, we could have had both. So first name is string, middle initial is an option of type string, and last name is a string. How do they do it? What do they call those types in Elm? I forgot.
The maybe, and there's a and then under the maybe is a just or a sum. A night, buddy. Just or a none or something like that. Love you too, buddy. See you. Good night. Yeah, so it's a maybe type, and the maybe they use what is it? Sum here, sum instead of just,
Right.
which is basically the same thing. And then I don't know what Elm. Whatever it is, it's none, or missing, or nothing, or something like that.
Yeah, I like the Elm name better, maybe, but it's fine. Option is fine.
Yeah.
So F# also supports using the option label after the type, which is easier to read and more commonly used. So middle initial string option. So how do we model errors? Let's say we have a. Oh, sorry. Do you want to take this?
No, go ahead. Keep going. This is good. It's all related, so keep going.
All right, let's say we have a process with a possible failure. The payment was made successfully, or it failed because the card had expired. How should we model this? F# does support throwing exceptions. We'll often want to explicitly document in the type signature the fact that a failure can happen. This calls out for a choice type with two cases. So let's define a type result. So we'll have a type result, which will have a generic success.
Yeah, because so the idea is that you want to create a result. So you give it your own success, like what to do on success and what to do on failure or whatever. And then that's your result type. And then if the thing that comes into it could be one of these two things, it could be a success or a failure, and depending on which one it matches on. You know what I mean? So like something fails. So if you have a try except somewhere and you spit out this type of success, whatever you want to call it, that's one thing. And if you spit out this type of failure, that's another thing. And you say that the return type of this function is a result of the success failure. And then you basically just match on it and given if it's a success, do this, given if it's a failure, do that shit. But the point is you can define your own successes and your own failures. So that's your result type.
Right. Well, let's see how this is used. I think it'll be easier, right? We'll use the OK case to hold the value when the function succeeds, the error case to hold the error data when the function fails. And of course, we'll want this type to be able to contain any kind of data, hence the use of generic types in the definition. If you're using F# 4.1 and above, all right, let's skip that, we're not. To indicate that a function can fail, we wrap the output with the result type. For example, if the payment invoice function could fail, then we might define it like this. Type pay invoice takes in an unpaid invoice, and a payment, and outputs a result of either a paid invoice or a payment error. Show that the type associated with the OK case is a paid invoice, and the type associated with the error case is a payment error. We could then define payment error as a choice type with a case for each possible error.
This is pretty powerful, actually. Now I'm realizing what, like, because you can just literally spit. You're saying, oh, it's a payment error, and then you have all these other, card type not recognized, payment rejected, all these different ways it could go wrong, right? And
Yep.
whatever result comes back, whatever type it comes back as, if it's one of them, it's a failure,
Yeah. Yep.
So that's kind of neat.
So this approach to documenting errors will be covered in detail in Chapter 10. Super cool. This deserves a lot more in depth.
Yeah.
Modeling is amazing when it's done well.
Yeah, for sure. Modeling no value at all. So most programming languages, this is one of the big differences actually of functional and non-functional stuff. Is most programming languages have a concept of void, used when a function or method returns nothing. So I'm thinking side effects, doing stuff.
Yeah.
In a functional language like F#, every function must return something. So we can't use void. Instead, we use a special built-in type called a unit. There is only one value for a unit, written as a pair of parentheses. Really quick, let me just run that right here. Like that, and that is a unit. Okay. Let's say that you have a function that updates a customer record in a database. The input is a customer record, but there's no useful output. In F#, we would write the type signature using in unit as the output type like this. Type save customer, it takes in a customer and outputs a unit. In practice, it would be more complex than this, of course. For a detailed, so working with databases, we'll get into that. Alternatively, let's say you have a function that has no input, yet it returns something useful, such as a function that generates random numbers. Remember how much of a pain that was in Elm? The random number, you had to pass it off to the runtime because the functions had to be pure and all. It's like, whoa, that blew my mind. But anyway, so you don't take in anything, you just have it spit out a random number here. In F#, you would have no input with the unit as well, like this. So type next random takes in a unit, in other words, nothing, and outputs some random integer. When you see the unit type in a signature, it's a strong indication that there are side effects. Something somewhere is changing state, but it's hidden from you. Generally, functional programmers try to avoid side effects or at least limit them to restricted areas of code like monads and whatever. Okay. This is interesting. I think you're going to have a lot more to say about this than I will. I read this last night and I thought of you. I was like, oh, he'll like this part. So it's good that it fell on you.
Keep going.
No, why don't you do this? That's what I'm saying. Like, I thought of you and I read this.
All right, let's see. I haven't read this yet. So modeling.
That's why it's great.
Collections. F# supports a number of different collection types in the standard language. List is a fixed size, immutable collection, implemented as a linked list. Array is a fixed size, mutable collection where individual elements can be fetched and assigned to by index. Resize array is a variable size array. That is, items can be added or removed from the array. It is the F# alias for the C# list T type. Sequence is a lazy collection where each element is returned on demand. Is the F# alias for the C# IEnumerable T type. There are also built-in types for map, similar to dictionary and set, but these are rarely used directly in a domain model. For domain modeling, I suggest always using the list type. Just like option, it can be used as a suffix after a type, which makes it very readable, like this. So we have a type order, that's a record, which includes an order ID, which is an order ID, and lines, which are order line lists. It's a collection. To create a list, you can use a list literal with square brackets and semicolons, not commas, as separators. Let a list equal to 1, semicolon 2, semicolon 3. or you can prepend a value to an existing list using the double semicolon, also known as cons operator.
Mhm.
Let new list equal to 0 cons operator a list, and now the new list is 0, 1, 2, 3. Now, we'll just note that you've created a new list. You haven't mutated a list. A list is still equal to 1, 2, and 3. Only new list is equal to 0, 1, 2, and 3. To deconstruct a list, in order to access elements in it, you use similar patterns you can match against list literals like this. Let print list 1 a list equal match a list with empty brackets and then print the list is empty. A single value, list has one element. Multiple values, list has two elements, or anything, a longer list, which is anything else. So we only
Yeah, but you could do better than that, I think. Because I was wondering, I was like, where is the head and the rest? And they do it
right,
next.
there we go.
Yeah.
So, or you can match using the cons operator like this. Match a list with empty and then print the list is empty, or match it with a first cons rest, which is a pattern match, which will take the head of the list and split it off the rest of the list.
That's cool.
And yeah, we should see that.
Yeah. I mean,
Well,
same.
let's do, why don't you make a list 1, 2, 3, 4, and then just pattern match first and rest.
Okay. Okay. And then just was it defined as a function?
I think you could just do let. I think it'll be clear enough if you just do let first cons rest.
What?
Do a list.
What's that?
I think you can do let first cons operator rest equal to.
Oh, got you.
Right?
Yeah. I
It
think
should work. I think.
think so. Doesn't like it.
Yeah.
I mean, oh. That's interesting. So the problem is, so this is actually, we ran into this kind of problem a lot with Elm. The problem is we don't have this empty case. So it's saying it's not a complete. Okay. So
Right. But I think it did it anyway. Like type first.
yeah, you're probably right. It probably did.
Yeah.
Yeah. So
It
yeah.
just said it's a warning. It doesn't like it.
Yeah. That's cool. Yeah, so if I had done the one here, it probably wouldn't have a problem, right? Because it's either going to be empty or it's going to be what we just gave it.
Right. It's
you know
basically saying you got away with it this time, boys, but it could have been bad.
Okay. Well, I mean, let's make it bad.
Could have been terrible.
Let's do a bad thing then. Let's see what happens. Let me even.
Oh, like look, you broke F sharp again.
Stop due to error. The match cases were incomplete. Yeah, I know.
You broke it.
Tried to
We
do it.
tried to warn you. We gave you a warning.
Yep. I wonder, it probably warns you. Yeah, it's probably a compile error too. Like if you were just to compile it, it'd probably be like, yeah, I don't know, man. Like, I don't want.
We're just trying to do some examples
here. Yeah. Okay, so this is this. I found this kind of interesting, but it's also sort of intuitive. But it's still interesting, and it would be you can see how this could be a problem if you don't pay attention to it. So organizing types in files and projects. There's one last thing you should know. F# has strict rules about the order of declarations. A type higher in a file cannot reference another type further down in a file. So there's literally higher up on top, in the file, line 5 versus line 50. And a file earlier in the compilation order cannot reference a file later in the compilation order. This means that when you are coding your types, you have to think about how to organize them, how you organize them. A standard approach is to put all the domain types in one file, say types.fs or domain.fs, and then have the functions that depend on them to be put later in the compilation order. If you have a lot of types and you need to split them across multiple files, you put the shared ones first and the subdomain specific ones after. Your file might look like something like this: common.types.fs, common.functions.fs, order taking types, order taking functions, shipping types, shipping functions. Within a file, that rule means you need to put the simple types at the top and the more complex types that depend on them further down in dependency order like this. So this type payment has to come after payment method type was defined. Payment method type has cases in it, and those had to come after they were defined, if they were defined, like the of check number and the card of whatever the other thing is going to be. When you are developing a model from the top down, the dependency order constraint can sometimes be inconvenient because you often will want to write the lower level types below the higher level types. In F# 4.1, you can use there was a note previously, that's Visual Studio 2017 and above. You can use the rec keyword or the I'm guessing it's like recursive or something at the modular namespace level to solve this. The rec keyword allows you to reference each other anywhere in the module. So module rec payments, so they put the payment, so the whole module has the rec, and they put the payment, it's almost like, why wouldn't you do that? But they put they say doing this is sloppy. Hold on, let me get there. Sorry, stopping myself. So anyway, so they define the payment at the top, and then the things that actually it depends on are actually defined below it. And they actually flipped the order exactly in here, but they could have been anywhere. So for earlier versions of F#, you can use the AND key. So for earlier versions without the rec, you use the AND keyword to allow the type definition to reference a type directly underneath it. So type payment has a payment method, and payment method comes right below it. And the wow, that's like that's like definitely recursive. That's why they call it recursive. Okay, I get it. And the check note, so it would go down here and it would go down to here, and then it would bubble back up. Okay, this out of order approach is fine for sketching, but once the design has settled and ready for production, it's generally better to put the types in the correct dependency order. This makes it consistent with other F# code and makes it easier for other developers to read. For a real-world example of how to organize types in a project, see the code repository for this book. I did not know there was a code repository, so okay. I will go searching for that. And then we're on the wrapping up.
All right. We learned a lot.
Definitely a good chapter, man.
Yeah. In this chapter, we looked at the concept of type and how it relates to functional programming. And we also saw how the composition of types could be used to create larger types from smaller types using F#'s algebraic type system. We were introduced to record types built by ANDing data together, and choice types, also known as discriminated unions, built by ORing data together, as well as other common types based on these, such as option and result. Now that we understand how types work, we can revisit our requirements and document them using what we've learned. All right.
Sweet. Yeah, so I don't know if you want to stop recording.
Take this one next time.